Welcome, everyone. Excited to share with you guys around our solutions that we're building specifically for media and entertainment, with a focus on how we leverage GPUs in our environment. And special thanks to Tom and Caleb for joining today. Really excited to get their perspective on how they view the world and how they view this technology helping their workloads. As mentioned, my name is Sumit Puri, CEO, co-founder here at Liqid, and let's go ahead and get started. There are two primary products that we'll talk about today here during our podcast. One of them is related to our software and architectures related to something referred to as composable disaggregated infrastructure. And then we'll also talk a little bit around some really high performance storage solutions that we are deploying with our composable architecture. And they are also great for standalone media and entertainment applications. And we'll spend a bit of time talking about that also. Let me start off with composability and kind of describe exactly what we see in the data center as far as data center transformation and data center trends. This slide is from Gartner. This is around the data center roadmap. Where were we? Where are we? Where are we headed? The two key takeaways we like to point out on this slide. Number one, in our opinion, statically configured infrastructure is not the future. We think the future is all around dynamically configuring the infrastructure at the bare metal to best match the workload that we're looking to deploy. The software-defined data center is where we think the endpoint is. And in order to achieve this goal of the autonomous data center, we think two fundamental technologies are required. Number one is the ability to disaggregate hardware. And then number two is to come in with intelligent software and reconnect or compose that hardware back into the server infrastructure that's best suited for the workload that we're looking to deploy. A lot of what we focus around is around GPUs. And as Jensen kind of stated, once we can disaggregate, recompose, and reconfigure, it's going to really change the way that we think about how we deploy very valuable data center resources like GPUs. I think the easier way to kind of think about this concept of composability is comparing it to what we refer to as legacy servers. In a legacy server, we take devices, a storage device, a networking device, these days, a lot of GPU devices, and we plug them directly into the sockets of the motherboard, and we define what our server looks like. And if we want to change that configuration, normally we're sending a human with a cart and a screwdriver, and we're manually moving things around. In a disaggregated world, think about pools of resources, pools of compute, pools of storage, very important pools of GPU resources. It doesn't matter what the endpoint is. Instead of taking that endpoint, plugging it directly into a server, we take pools or trays of these devices, we connect them into a switch, and then we come in with software and we dynamically configure our server at the bare metal. Take that 1U R640 pizza box, R650 pizza box, take 8 of those storage devices, give me 12 NVIDIA GPU accelerators, connect them all together at the bare metal, just like I was putting the devices into the sockets of the motherboard, but except we're defining it in software, we're reprogramming the switching layer, and on the other side, we're getting delivered servers, however big or small we want our server to be, except the server is dynamically reconfigurable. So when my M&E workload needs another GPU, we're not sending a human with a screwdriver to try to squeeze that into a server. We're sitting back from our desk, we're reprogramming the fabric, and we're adding or removing GPUs from the server, depending on what the admin, the user, or what the application layer requires. And all Liqid builds here is that software that allows you to orchestrate, a little bit of the hardware that allows you to disaggregate, but we partner with companies like Dell so that we can deliver you guys the complete solution. And that at the end of the day is what we're focused on, is partnering with Dell and partnering with Frame Labs and coming up with solutions where we can go solve problems that leverage this composable architecture. And there's a lot of different reasons why customers are moving towards a disaggregated architecture. I think dynamically moving a GPU from server number 1 to server number 2 is easy to understand, but there's a lot of additional benefits when we move to this kind of architecture. Number one is if we can increase the utilization rate of the hardware that we are buying, in theory, we may be able to buy less hardware. If I can move that GPU around to any server that needs it whenever it needs it, maybe I only need to buy 50 GPUs and not 100, right? We can reduce not only the infrastructure footprint, but we can reduce the power, the cooling, the water consumption, all of the other benefits that come with improving that utilization, right? There's no bigger knob than we can turn inside the data center around TCO other than utilization rates. We can create what we refer to as impossible configurations. If we need a Dell server with 16 GPUs inside of it, that's probably not a configuration where sheet metal is bent to be able to go do that. But we partner with Dell today and we deliver 16, 17, 20 GPUs to a single server if that's what the application requires. And as soon as that application doesn't need all that hardware, we can move those devices around to other parts of the infrastructure, right? We can change the way that we scale out. We can add trays of just accelerators without paying for additional networking, for example. So the most efficient way to scale out our data center is through a disaggregated fashion. And we can spend a lot of times, going into each one of these. But, what we like to point out is that, there's a lot of interest in this and it's working, right? And there's a handful of use cases where we see traction in this solution, right? And so number one, I would say is AI and machine learning and deep learning and those quintessential GPU workloads, right? We can make them run faster. We can make them more efficient. We see a lot of traction in HPC. HPC, has a lot of different workloads deployed onto the machine. Different workloads require different hardware profiles. We can study the workload on the inbound, spin up the t-shirt size, small, medium, large, match that workload to the perfect amount of infrastructure. We do a lot with companies who are still wanting to own and operate clouds, right? We bring the dynamic agility of cloud to infrastructure that our customers are owning on-prem. We think edge is a massive opportunity. We think that's where all the data is actually created. And eventually the compute, the GPUs, those resources will move closer to the point where the data is actually created because it's difficult to forklift large quantities of data and move it. And so we'll move the GPUs and the compute closer to the data. And then as mentioned, media and entertainment. Media and entertainment inherently can benefit from high performance storage, large quantities of GPUs, more efficient use of GPUs. And we'll walk through a couple of use cases around media and entertainment where we think this matters. I think a lot of our customers are not trying to figure out is dynamically reconfigurable better, is static better. I don't think that's necessarily the argument, right? I think customers, partners, architects, everybody understands dynamic is better than static. I think a lot of our customers are just trying to figure out, am I going to own infrastructure? With the dollars that I have available, am I going to give it to AWS or am I going to own infrastructure? And the value proposition that we bring is we can give you the agility, the flexibility, the dynamic capability that you would have gotten on public cloud, except we give it to you on the infrastructure that you own. We give you much higher levels of performance, and we can save you a lot of money doing it also. I think the economics of moving GPUs to a composable nature is very powerful and very meaningful. And today, I would say majority of the workloads that we are deploying against today have something to do with accelerators. We think, past workloads were very compute centric. We think future workloads are going to be very accelerator centric. And the platform that we've developed here, really some of the benefits are around scaling GPUs. I need to build a system, it needs to go really fast. I need 8 of these things, 10 of these things, 20 of these things, all connected to a single compute node. And we can scale out either to a single compute node or inside the data center. We can share these things. When compute node 1 no longer needs that $15,000 accelerator, let's move it around to a different compute node so we can get maximum utilization out of it. We'll show you some numbers. We can go fast. This architecture, not only is it flexible, but it's very performant also. And if we need to build the world's fastest AI machine, the world's fastest video rendering machine, we can do it because we're not confined by the amount of hardware you can squeeze into a single piece of sheet metal. And I tell this to my team all the time. I don't think we would sell $1 of this stuff if there was not a compelling cost benefit to the customer. And I think that is probably the most important thing. Accelerators are expensive. Accelerators are power hungry. As we go forward, they're going to get more expensive and more power hungry. So we must come up with more efficient ways to consume these devices. And we think enabling a mentality where we can share these devices throughout the data center, we think that makes a lot of sense. I'll walk through just a couple of use cases here, and then I'll flip to the physical layer and show you how all of this stuff actually interconnects. We'll walk through a little bit around performance and software, and then we'll make sure we leave time for questions later. A lot of people are talking about AI, right? Everywhere we go, people are talking about how they're trying to figure out how to leverage AI in their environments. And I think one of the things we like to point out is AI is not an event. We don't go do AI. AI is a series of operations that leads us to some kind of outcome. Normally, the AI workflow, as we like to talk about it, starts with data ingest, right? I'm bringing data into the environment, and that's a network-intensive activity. I need lots of NICs to go do that. Then we move on to the preparation of the data, the cleaning, the tagging, the scrubbing of these large quantities of data. And that actually is a compute-intensive environment. I need a lot of CPU horsepower to normally go off and do that. And then I move on to my training part of the algorithm. This is where I need my 8-way, big, beefy machines that have lots of GPUs so I can crush my training times. And then after that, I move on to data inference, right? This is the practical implementation of potentially what I learned during the training part of the workflow. And that, again, is like a single T4 GPU, a completely different hardware profile. And you have these large data sets that sit at the center of the universe. And many times we're shuffling this data amongst different machines. We like to take a slightly different approach to this, and we like to put the data at the center of the universe, and we bring in the compute horsepower when we need it. We bring in the GPU horsepower when we need it. And when that server no longer needs those accelerators to do his training piece of the process, we can free those accelerators out and let somebody else use them for training, for example. So we think the dynamic capability applied to things like AI workflows makes a lot of sense. Let me move to the physical layer here and show you actually how all the hardware interconnects. And then, we'll show you a little bit on the software. And so with these three fundamental building blocks and the servers that Dell builds, we can build everything from a small pod of infrastructure to very, very large deployments that take 30, 40, 50 racks of infrastructure. And so these building blocks, it starts with our software, Liqid Command Center, and this is how we do the orchestration. The next building block is our tray for GPU disaggregation. We refer to this as a JBOG, just a bunch of GPUs. This is not a server. This is a PCIe expansion chassis, and we can deploy GPUs inside this expansion chassis. Think about a 4U box that holds up to 10 NVIDIA or GPU accelerator cards. And then we have our tray for storage elements, right? And so it's a 1U box where we can deploy storage devices, or we can actually deploy storage class memory. It starts with really, really simple deployments that look like this, where we take a small PCIe card, we plug it into the Dell server, we connect that Dell server over to one of our PCIe expansion trays. And in this example, I have given that Dell server 10 GPUs, for example, right? As far as the server is concerned, the operating system is concerned, the application layer is concerned, all of those GPUs are locally connected on the motherboard of that Dell server. We don't put any software, any drivers, any hypervisors. It's your compute node. You can run whatever application you want on it. Our guarantee to you is if your application worked on a quote static server, your application will work code unchanged on something disaggregated. And so this is the most simplest use case, just around GPU expansion, where we've taken a 1U server and we've given him 20 GPUs or 10 GPUs. And then we can get more complex from there. And so this is an example of GPU sharing, where we have 16 servers, Dell servers in this example, connected to one of our expansion trays. And then we come in with software and we dynamically assign accelerators to hosts. So I can say, take 2 of these A100 GPUs, connect them over to server number 2, make that association for a minute, a day, an hour, a year, however long you want. And as far as that server is concerned, Those are just locally connected GPUs on his motherboard. He can't tell that we're grabbing those from a disaggregated tray. And as soon as we don't need those GPUs in that server anymore, we can reprogram the fabric and either put them back into a free pool or move them over to server number 15 dynamically. And when we say dynamically, we're actually talking about hot plugging or hot removing devices from running servers. We don't even need to power the server down if we want to move these accelerators in between the different hosts. And so this is the next level example where we're sharing a GPU pool with a large quantity of hosts. And then from there, we can build bigger, right? And so in this example, I have my pool of compute, my pool of accelerators, my pool of memory, and my pool of NVMe storage. And so if I need to go create that, super fast, high performance machine, great, I can go do that. I can take this compute node, I can connect 10 GPUs, half a terabyte or 2 terabytes of memory, and a half petabyte of flash, connect it over to this server. It will run at line rate, just as if those devices are directly onto the motherboard. And again, when we don't need that association anymore, we can reprogram the fabric, move the devices around the data center, and drive the utilization rate up, drive down the expense is our intention here. And then we can build bigger, right? And so as we build out, think about pods that can be anywhere between 1 to 3 racks of infrastructure. And so in this example, we're actually using 2U 4-node compute from Dell. Normally in a 2U 4-node server, how many accelerators can you put in the box? Well, the answer is 0 because there's no physical space to actually do that. But what that provides for us is incredibly high density compute. And so in this example, we have high density compute paired with a large pool of memory, paired with a large pool of storage, paired with a large pool of accelerators, and then all tied together with our fabric technology. And so in this example, if we need to create a high memory node, we can go off and do that. Take one of these servers, carve out as much memory as we need, connect it, and I've built myself a high memory node. If I need a high GPU count node, we can go do that, right? Again, study the workload on the inbound, decide how much infrastructure we need, spin up our t-shirt size, small, medium, large. That is how we drive maximum utilization of the hardware. One of the questions we always get asked when we show this is, tell me about performance. How does the performance work? How does the performance scale? And so here's an example of us taking a standard Dell server and scaling up to 20 RTX GPUs to this server. And what you see here is we get great linear scaling, right? And so not only are we able to add large quantities of accelerators where they're needed, we're also able to deliver very, very linear performance as we scale up. And so in this example, a 1U server with 20 GPUs delivering massive levels of performance. Another question we often get asked is around drivers, and the answer is there are none, right? We don't put drivers, modules, hypervisors, none of that goes onto your host. It's your host. You can run whatever operating system you want. This is an example of just plain vanilla Windows, and we have connected 20 RTX 8000s to this 1U server, and the devices show up under Device Manager just as if they were locally connected. And if we were to move those devices away, you would see those devices disappear under Device Manager. So no special operating system or drivers required to make it work. It's all plug and play. The other question we get asked is, tell me around performance in the box versus the GPU performance outside of the box. This data was actually collected by the Dell CTO office. And so what this is showing, the orange bar, is a disaggregated GPU or a composed GPU, and the blue bar is a static GPU deployed directly inside the R740. I think the takeaway from this one is it's the same, right? There is no performance delta if you run in the box or if you run in a disaggregated fashion for a very simple reason. We disaggregate over PCIe. Our PCIe latency is 100 nanoseconds per hop. So at the application layer, you are not going to be able to tell that we are disaggregating because the latency over PCIe is measured in hundreds of nanoseconds. So, we have really good luck here. in being able to deliver performance that's comparable or the same, and in many cases higher, because we can put more accelerators to the task than a static server with the devices directly in the box. We talk a lot about our stuff, but I think it's important for customers to speak on our behalf also. And so we like to point this one out. This is one from Orange, Silicon Valley, where they did a blog where they think they have the world's fastest, ResNet node, built around a Liqid architecture. And it was quite simple, right? They were able to get 16 GPUs connected to a single compute node, enable advanced features like peer-to-peer technology, and really able to deliver some super high levels of performance, and be able to do it at a cost budget that was more attractive than some of the other solutions they were looking at. I'll talk a little bit about the software now. I do definitely want to leave time for the others to speak and for us to answer questions as a team. But let me explain a little bit how we pull the strings of the fabric, or how we manipulate the hardware. There's three fundamental ways that we can move the hardware around. The first way is we have a GUI. It's a very intuitive GUI. It's click and drag. It's as simple as just clicking a GPU, dragging it over to a server, letting go, and we have assigned that GPU over to that server. A very simple way to use our infrastructure. The GUI is built upon a REST API. Every keystroke in the GUI is mapped to a call on REST, and we give our customers full access to the REST API, a full Swagger interface, so they can just pick up any scripting language they want, for example, Python, and start writing scripts that say, for example, at 10 o'clock at night, when I know no one's using those GPUs, pick them up and go move them to those other servers so I can run some video rendering workload at night, right? And so we can set up policies, based upon scripting on the things that we want to do. The next thing we do with our API is we integrate north. We integrate the tools and the frameworks that our customers use today. In HPC GPU land, there's a workload manager called SLURM that's very popular. We take our API and we integrate with SLURM. We integrate with VMware. We are integrating with Ansible. Integration for Kubernetes is coming, right? And so integrate into all of the orchestration tools that our customers are using today so we can make this stuff easy to use. One of the big ones that's very popular for us is around SLURM. SLURM is a workload orchestration engine used many times in high performance computing environments. And the way SLURM normally works is SLURM comes down to the infrastructure and says, I have a job, I need 4 compute nodes with 2 GPUs apiece. And if the best match of infrastructure that we have is 4 compute nodes with 4 GPUs apiece, well, it's up to the admin on whether I'm going to run that job and potentially have a bunch of GPUs underutilized, or am I going to wait for some better matched infrastructure to come up? In our world, SLURM comes down to the infrastructure and says, give me 5 compute nodes with 5 GPUs apiece. A configuration that probably doesn't exist in the wild. We go into the backend infrastructure, we create that exact configuration that SLURM has requested. We give those compute nodes over to SLURM, and it's happy because it got the exact hardware that it wanted. And the theory is less wasted infrastructure per job means we can run more jobs in parallel because we can drive our utilization rates higher. Another big integration we have is into VMware. Often we get asked, is there I'm doing, composability now. Does that mean I don't need virtualization anymore? And that's not the way that we look at it, right? And the way we think about it is virtualization is a phenomenal technology. VMware is an amazing company. Their solution works great if I deploy it on top of a static box, but it works better if I can deploy it on top of disaggregated infrastructure. If the hypervisor can reach down to the infrastructure and say, give me another SSD, I want to slice and dice, give me another GPU, I got this VDI thing that I want to take care of. We think the marriage of the two is really how we get to a 100% resource utilization inside the data center. The old model is I buy a box, that box has 8 SSDs, for example, inside of it. When I need the 9th SSD, I buy another box and I pay for more VMware. In our world, it's not like that. When that server needs the 9th SSD or another GPU, we compose that hardware underneath the hypervisor, and the hypervisor can't tell that those elements are disaggregated. It thinks they're local to his motherboard. And so just as we can raise efficiency and utilization, save money on hardware, we think there's a similar benefit here around software. Last couple of slides, and I'll kind of hand it off to the others. One of the advanced features we support in our software is the concept of hardware containers or machine containers or templates as we define it. Think about it like this. I may have 50 pieces of hardware, but I can reconfigure that hardware 200 different ways. So if I'm going to go run something like a tensor workflow container, I actually know the hardware I want for that, right? And so I can predefine that hardware as a template. And then when I'm getting ready to launch my software container, I can have that predefined hardware profile. So with one click, we launch the physical infrastructure. The next click, we launch the software that's perfectly matched for it. Today it is, and this is like the kind of the vision slide here, right? Today it's very much a user-defined world. I come in as a user and I say, give me a server that looks like this, right? This amount of storage, this amount of compute, this amount of GPU. From a user-defined world, we are moving to a policy-based world, right? So when I create that server, I start dictating the behavior of that machine. When the server goes above 80% storage utilized, automatically reprogram and give him more storage. At 9 o'clock at night, when I know nobody is using those GPUs, strip them off and go use them for some video rendering application, right? You know, policies based on time of day, policies based on performance, policies based on utilization, policies based on failure domains, right? If the DRAM on the server fails, let's take his NICs, his GPUs, his storage devices, and move them over to a spare server, right? We can create a policy for that. And so policy is where we go next. And then eventually we get the human out of the way completely, right? We move to a machine learning environment where the machine learning is studying the usage patterns of the hardware, and the machine is determining when to turn the knob for more storage and how to drive maximum utilization. And so I think that's eventually where we end up. That machine learning piece of it is how we get to the lights out, autonomous, software-defined data center of the future. But it's a journey, and we're excited to be taking it with partners like Dell and Frame Labs. And then I'll close with this one because I think it's important, right? There's a tremendous amount of waste, right? There's waste in non-productive servers. There's waste in oversizing our servers. There's waste in idle times and inefficiency, right? And we think this has a direct impact on things like power, cooling, water consumption, the sustainability aspect of it. And I think until just recently, sustainability was a nice topic to discuss. Now I think it's becoming, you know, a critical thing that we have to talk about, and purchasing decisions are being made around it. Couple of just interesting statistics, right? A megawatt of power in the United States is about $1.5 million a year. In Europe, it's 2 to 5 times that much because of the energy crisis. A megawatt of power consumes 8.5 million gallons of water per year. Many of us who live in the West, we know how real the water problem is, right? And so we think it's going to be demanded, required, and we have to do it as an industry, is move to more efficient solutions. And we think there's no bigger knob than we can turn on efficiency than utilization rate. And so we think dynamic infrastructure will enable very high utilization rates of hardware. And we think that's going to become a really, really important story going forward. I just thought it was important to talk about that. I'm going to move very quickly through our storage fabrics product because I think it's relevant for media and entertainment. And then I'll switch over to let Tom and these other guys talk about some of the things that they're seeing. Liqid also builds a couple of high performance storage devices. They come in an add-in card form factor. We have a Gen 3 product, which is a 16 terabyte card, which comes in a half height, half length add-in card form factor. We also have a Gen 4 product, which is 32 terabytes of storage capacity with a Gen 4 by 16 interface. And that is a full height, full length add-in card form factor. The way that we achieve this is through our PCIe fabric technology. Rather than building these devices off of a single SSD controller, what we've done is we built a PCIe fabric where we're able to aggregate up to 8 of these SSD controllers onto a standard form factor card. And then we overlay enterprise class features like power loss protection, enhanced monitoring, so that we can deliver something that's not only high capacity, high performance, but has all the enterprise class features that our customers would want. This product is being sold through Dell, and the primary benefit of this product really is around performance and capacity. So this is the highest performing NVMe storage device on the market today. It can be used with our composable architecture, or it can be used standalone inside of a Dell server. And so ultra levels of performance, the vendor A, as you see on the screen there, is the next highest performing NVMe solution on the market. We're 3 to 4 times better performance out of the solution, and much, much higher levels of capacity. It's a plug and play solution, so it will work with any operating system plugged directly into the server. Really, the benefit of this is around performance consolidation. We're giving you the entire performance of a SAN out of a single, add-in card opportunity. Where this applies directly is to high performance applications. One of those is around virtualization. And this is just a very simple example to explain the kind of benefits of performance. I think, performance is always interesting. Performance is always a good thing, but unless you can tie that performance back to some financial benefit, I think it's always just a nice to have. And so I think it's important to make people understand that with performance, we can actually do more with less. And so in this example, we have a VM environment where each VM requires 50,000 storage IOPS of performance. And so if we have a storage device that can give us 450,000 IOPS of performance, we're going to be able to service 9 VMs. With our solution that can give you 2.5 million IOPS of performance, we can service 50 VMs. So if you want to service 50 VMs, do you want to buy 5 storage devices, or do you want to buy 1, right? And so we think there's a consolidation play here around performance. Similar idea around video streaming, right? If we have a slow performance device, we can support a certain number of streams. With an ultra performance device, we can support a much greater number of streams. So again, performance for the sake of performance is not good. Performance for the sake of infrastructure consolidation is meaningful. And we've done white papers with Dell on this. We have a really interesting product. Our product is called the Honey Badger, but in partnership with Dell, we've launched a reference architecture called the Badger Den, where it is the world's fastest storage server, right? We think there's nothing on the market that can touch the level of performance that we've delivered out of that machine. We can deliver up to 5 of our Honey Badger cards inside of a single Dell server. And so we'll share this link out. We encourage you guys to learn more, not only about our composable solution, but also about our high performance storage solutions, which are very well suited for media and entertainment opportunities. And with that, that's our presentation. I'd love to take this opportunity to introduce Tom Burns. Tom, I'll just say a few words on him, and then Tom will hand it off to you. And if you could introduce yourself and share some thoughts, that'd be great. But Tom is the CTO for Dell's media and entertainment business. He's been doing this, a long time, and has a tremendous amount of knowledge, everything from post-production and workflow requirements for media and entertainment. He's built VFX facilities in Shanghai, and built broadcast facilities in Manhattan. And he started his career back at Silicon Graphics, and has tremendous knowledge and depth here around media and entertainment. So with that, Tom, I'll be quiet here, and we'd love to hear a little bit about your background and have you share some thoughts.
Thank you very much for that kind introduction, Sumit. The only thing about my background is that I'm old and I've been around for a long time. But that actually informs what I'm about to say, because the best thing about my job is being able to go out to customers, see what they're working on today, and see what their worries are for the future. And so when Sumit showed that transformation of the data center slide, that seems very apropos to me of what's been happening in the media and entertainment business. From a monolithic machine room that was all based around real-time networks, not file transfer networks, but real-time video. That was kind of the equivalent of the old 3-tier architecture in the data center. And then we moved to hyper-converged infrastructure, which is when you get, all of these built-in appliances that do things like transcoding might be a good example. And so as we move towards the composable disaggregated infrastructure, we've got those 3 legs of the triangle. We've got the compute, which is GPU or FPGA. We've got the storage, whether that's an onboard Honey Badger as a tier. What's less than tier 0? The speed of light tier that you need for certain ingest and playout functions. And so between the compute, the storage, now the thing that differentiates this media and entertainment transformation from the data center transformation is we're starting to realize that even 100 gig or 400 gig networking is not enough. And so I want to encourage you to start thinking about the PCIe switching that Liqid does as the new way of doing networking at the edge. I mean, even with like 100 gig NIC and RDMA and all of the tricks that we can do to get Ethernet networking moving as fast as possible, there's no way that we're ever going to get down to 100 nanoseconds latency. And so if you start thinking about PCIe as the new network at the edge, then what you've got is your compute, your storage, and your networking all in this CDI framework where you've got a Dell server, you've got a Liqid PCI switch, all of the director stuff, and the chassis. Now, we've been talking about filling one of those chassis, is that even a word, with 10 GPUs. In my opinion, you should save 2 slots for 200 gig ConnectX 600 gig NICs, because they have the DPU on them that lets them do very low latency RDMA, regular Ethernet still. But the idea is, how regular Ethernet, every time the NIC receives a packet, it has to bang on the CPU for an interrupt, right? And so getting a server that can actually serve or receive 100 gigabits, that's like 10 gigabytes per second wire speed, just averaging out for the math. And there's just no way that you can get down to that kind of latency. So our data center model holds up really well, and yet we need the ability to come in from some mass storage. Like the Honey Badgers are great, but they're only 32 terabytes. So we need something to come in from a mass storage device, preferably over 100 gig RDMA enabled NIC, because that way you're not banging on the CPU all the time. The each packet, whether it's media or instructions, comes in through the NIC, travels over the little short bit of the PCI bus inside the Liqid chassis, or the Liqid fabric, I should say, without banging on the CPU. It goes directly from the NIC to the GPU. And that is something that no typical data center architecture, whether hyper-converged or otherwise, can even hope to touch. Now, we've been through this before with InfiniBand and things like that. And there's always, media entertainment, I said this before, it's all about best of breed. And so if you have the right compute, whether that's the right GPU model, if you have the right NIC, if you have the right PCI fabric and all of that, then you start being able to go through all of the points that Sumit made earlier about the goal is just to make full use of the resources that you have. And so at Dell, they have a phrase that they say, where the future is software defined and hardware accelerated. And I really can't think of a better example of how that model is working than when we look at the entire Liqid system with servers, with switch, with 1, 2, or 10 chassis. That's the way that the performant edge, the hot edge that's now the data center equivalent of what used to be the artist's creative bay, that's where the work happens. And that's why we think the Liqid architecture is the best thing to take media and entertainment forward into the future. So that's all I have for general trends. I'm going to turn it back to Sumit or George for the rest. Thank you.
Thank you, Tom. Appreciate that. That was wonderful insight. I think we'll save questions maybe for the end, but maybe let's give an opportunity for our next partner to share a little bit. So Khalib from Frame Labs, please, we would love to hear a little bit from you on your background and maybe some of your thoughts on what we've been discussing today.
Of course, thanks. I'll just give a brief background on Frame Lab Studios. We're a pretty small boutique visual effects facility in Vancouver, BC. We primarily work with pretty heavy in FX CG sequences for streaming and network shows. We fluctuate between 15 to 25 artists, usually highly specialized artists, very senior, and try and like punch above our weight in terms of small teams working together to do really high-end work in pretty short turnaround times. How our infrastructure is currently composed here is we're primarily a Rocky Linux-based studio with a few Windows workstations, and we have all of our hardware is all on-prem. We've only really connected to AWS for cloud rendering in those absolute 911 scenarios where the client needs something the next day and it just has to happen. We mostly utilize Maxon Redshift for our rendering, which is a fully GPU-based renderer. So we're a pretty GPU-forward company. I would say before Liqid, we plugged GPUs into every available PCI Express slot at every workstation. Before Liqid, what we actually did is we had at least dual GPUs in every single machine, and regardless of department, it's a dual GPU workstation, just so at night, every single workstation and render node could render as much as possible. But what we've been noticing is the request for GPUs is kind of going up outside of just lighting and rendering. Our environment department has been utilizing Unreal Engine and other AI tools like Stable Diffusion. And they're requesting high VRAM GPUs for some of their work cases. We've also had some of our compositing artists starting to use Nuke's inference node to do AI training. We're doing automatically generated garbage mats and roto and paint tasks. And they're requesting higher GPUs for some of their work cases. Even some of our texture artists are starting to use AI tools to generate seamless textures. And so what we're getting is we have our base build for each workstation, and then we kind of run into areas where we need specialized GPUs for specialized tasks. So generally, most every artist is pretty comfortable working with a single 8 gig GPU, either that's a Quattro card or an RTX card. But when we're running into big 4K plates that we're running AI tools on, we need much more VRAM. But it tends to be in more of these smaller cases. So instead of us needing to kind of go out and completely buy new infrastructure and upgrade all of our GPUs, what we've been able to do is throw a few GPUs into the Liqid chassis and then hook that up with our existing Dell R740s. And we can compose the infrastructure for the particular tasks and for the particular work case in those like more niche use cases. For example, we have really large cloud, like physical clouds that need to be rendered with all VDBs. That's a type of workload that can only live in VRAM and it cannot go out of core. And so we'll need NV-linked GPUs for just that. But they render super quick, so we don't need every single render node to be able to do that. And so what we'd be able to do is actually even mix RTX cards, like gaming cards, with Quattro cards in the same enclosure with Liqid, and then compose them for exactly what we need. So if we need a high GPU, very fast rendering, we actually utilize gaming cards. We get better performance with the higher clock speeds on a gaming card. If we have a workload that's more AI based that needs a lot of VRAM, we'll utilize NV-linked Quattro cards for that. And we've never been able to do mixing like this on the fly without somebody physically running around and moving GPUs, which we did have to do in some use cases. The other thing that we've been able to utilize with Liqid is all of its scheduling through its API. So at the end of the day, if somebody is not utilizing a GPU, if they're gone home for the day, we can move all of those GPUs back onto a single node. So we can go beyond 8 GPUs on a single node for one of our rendering nodes. What that means is we actually don't need as many licenses for rendering as we used to. You know, before we kind of capped out at 1 to 2 GPUs per node, and that would occupy a render license. But now, because it's mostly a GPU task and doesn't utilize as much CPU, we can basically create these impossible rendering nodes with 8 or 16 GPUs in them, render everything super fast, and greatly reduces our license cost. It also allows us to potentially mix up which renderer we're using. So we're primarily Redshift, but if we need a particular feature of another renderer like V-Ray, we don't need to go buy 25 V-Ray licenses. We can actually just buy 1 or 2 and then compose a workstation with a lot more GPUs and utilize it. And it's a huge cost savings for us. Liqid's kind of been really easy to integrate into our current workflow. It's treated just like bare metal for us. And so instead of us trying to go out and build more workstations and find exotic GPU enclosures that we can keep adding to, we can just get their GPU enclosure and hook it up to our existing servers. That's great because now we can scale up. If we need another 8 or 16 GPUs, we can add that to our existing infrastructure without anything else. We can just add GPUs as long as we have enough space for those like Liqid HBAs to connect into the fabric. The last thing I kind of wanted to talk about is kind of our cost savings from Liqid. We haven't needed to utilize AWS since we've integrated it. And the main reason is because our CPU and GPU utilization has gone up dramatically. We can really maximize every little bit of CPU and GPU for jobs. So now when we have like a really difficult render task that was going to take hours a frame, we can compose this crazy workstation, get an artist to be look deving with 8 or 16 GPUs, and almost have basically real-time or instant results. So we're lowering our labor cost for a task that could take 8 to 10 hours to look dev a particular asset. We can cut that down to 4 because they're essentially working with 5 or 6 times the hardware that they would normally have access to. So there's been other kind of cost-saving areas that we found. We've primarily been playing around with the GPU aspect of it, but other areas of composability that we've been finding to be really useful is with moving around mounted drives. So if we have a very large effect simulation, these simulations can be in the tens of terabytes, we can actually mount a drive, simulate it to that local drive so it doesn't occupy any network traffic. And then once that job completes, we can have a follow-up script that remounts it back onto the main server, and then all of our other render nodes can access it. Or that CPU-based only effect simulation, we can simply add GPUs onto it and then utilize it as a render node and render that same job. That takes tons and tons of bandwidth it opens up off of our network. And so instead of things being slowing down with big effect simulations that are generating all this data, we can kind of move that data onto the Liqid fabric instead of it going through our traditional 40 gig network.
And on behalf of Liqid, Frame Lab, and Dell Technologies, I definitely thank you for investing your time today to learn more about how composability can help deliver performance and efficiency for M&E environments. And we hope to talk to you soon. Thank you.